Okay. So hopefully now we're going to segue beautifully from genes to brains. So I'm going to take you through some of my research into cognitive neuroscience. So very much interested in the brain and how it develops as part of the aging process. So in terms of today's themes, I'm going to walk you through a little bit about the aging brain and talk to you about plasticity and how that changes as we move through the lifespan. I'm going to talk to you about non-invasive brain stimulation as well. So I use a technique known as transcranial direct current stimulation, or tDCS for short. So I'm going to talk to you about what it is, how it works, and also why we should be using it. And just at this point, if I say non-invasive brain stimulation to you, if there was an advertisement asking whether you would participate in such a study, can I have a show of hands of who would be a willing participant? Be very honest if you're not. Okay, so I'd say probably about a third of you would be willing guinea pigs at this point. Okay, hopefully we can change that towards the end of the presentation. And then I'll dive a little bit into my research application. So what existing findings are actually out there already. And of course, the very important participant experience. Okay, so I've got a bit of a demonstration coming up for you, what that experience looks like for anyone who comes into the lab for such research. Perfect. Okie dokie. So if we're thinking about the aging brain and just aging in general, what changes do we think occur with age? So that's across any kind of cognition or physically as well. How do we age? What are the noticeable signs? Feel free to yell things at me. Wrinkles. Yeah, yes, absolutely. Wrinkles, I've heard. Brain shrinkage, yeah. Grey hair, yeah. Slowing down. Slowing down, yeah. Joints. Joints, yeah. I feel that already in my 30s, yeah. Hearing loss, absolutely, yeah. Mm-hmm. Spine curvature. Curvature of the spine, absolutely. Any more for any more? Memory problems. Memory problems, absolutely. Not working. Yes. Yeah. So I'm hearing a lot of negativity around aging, and that is absolutely where we tend to jump to in the first instance. But hopefully I'm about to persuade you that aging is absolutely not all negative. It's a dynamic process of change. And the more we can embrace that and the more we can help older adults to age well, to maintain cognition for as long as possible, the better. Okay. So, of course, being a cognitive neuroscience, I couldn't not show you multiple pictures of brains during this talk. So, what do we notice the difference between the left-hand side panel and the right-hand side panel? Any differences there that are super obvious in terms of the brain? So one brain is of a 20-year-old, the other is of a 70-year-old. Can we guess which is which, first and foremost? They are both healthy, yes. Which do? Yeah, so left is our 20-year-old, right is our 70-year-old. What do we notice in the differences? Pardon? Holes, yeah. To put no too fine a point on it, we've got noticeable gaps in our 70-year-old's brain. So we have, if I can we see the pointer? No? Okay, I've got no pointing devices here, but we can see around the top of the green image on the left there, there is space which is being filled with cerebrospinal fluid instead of our grey matter brain tissue with our neuronal population. So we're losing volume of the brain. And in the centre there, you can see the ventricles have expanded as well. So again, a signal that we're losing mass in our brains as we move through the lifespan. But of course, I'm trying not to err on the negative side of things here. The brain is absolutely fantastic at functionally reorganizing itself as we get older. So we might see things in terms of perspectives on decline, loss of brain tissue, expansion of the ventricles, for example. And it is largely a period of what we might refer to as structural deterioration in that respect. But there's also a lot going on behind the scenes. The brain is rewiring itself to try and maintain cognitive function for as long as possible. Okay, so you can see that as an example at the bottom there. So again, the left-hand side is brain activity from a functional magnetic resonance imaging scan from an attention-related task. On the left is our younger adult. Their brain activity very much lateralized to one side of the brain, okay, in the right hemisphere. However, on the other side, on the right-hand side, you see a spread of activity. So whereas in the younger adults, activity is very much lateralized to one side of the brain, we see that spread or asymmetry, lack of asymmetry in our older adults. So it's not just the right hemisphere that's becoming involved, it's the left as well. So we see a real division of resources. So we know that resources might be declining as we move through the lifespan due to loss of brain tissue, for example. But the brain is fantastic at pooling whatever resources it has together to try and keep up with things, to try and keep pace with our younger adult selves in terms of memory tasks, attention tasks, decision making, any kind of number of executive challenges that we could choose to throw at it. So, bottom line here, we have an incredible ability to do as much as possible with the limited resources that we might have as we move through the lifespan due to this compensatory mechanisms and due to neuroplasticity. So again, brains are absolutely brilliant, and we do have these resources that we can try to muster together to keep us functioning for as long as possible. So aging, absolutely not all negative stories to be told in terms of our brains. Okay, so of course, in terms of supply and demand, it might be that further through the aging lifespan, such neural flexibility and cognitive flexibility that we have to make these changes may not be sustained in the long term. So this might last through our 60s and 70s, but then as we're increasingly living for longer, as we reach our late 70s, our 80s, this cognitive flexibility might not be sustained in the longer term. So then we have to think that as plasticity starts to deteriorate as we reach older adulthood, these compensatory mechanisms that we have might become saturated, and we might then start to see cognition declining. So where we mentioned slowing down, memory changes as well, that's where this can all really start to come to the forefront. But of course, then that might mean that interventions are going to be needed to try and support our existing resources for as long as possible, to strengthen and bolster what we have to give our brains that helping hand that it needs. So can anyone think of any ways that we as individuals can help ourselves age better in terms of brain health? Keeping active, yes. So anyone who's going to the gym, running, doing any kind of physical activity, you're actively helping your brains to do better throughout the lifespan. Anything else? Yeah. Absolutely. Any kind of mental activity, mental flexibility, puzzles, the harder the better, the more complex the better. I hear dancing is an incredible way to keep the brain flexible as well. So we heard about music in mind and singing, which is very much engaging for the brain and keeps us socially active as well. So social interaction, very important. But dancing, not only have you got that physical component, but you've got the mental dance steps, keeping everything in time. And as well, if you're doing that with a partner, social activity. So we're thinking about anything that's biological, psychological or social to keep us cognitively flexible as we age. But there might be a time when external interventions are also needed. So if we're doing all of these wonderful things for ourselves, are there kind of external means that we can use to also give our brains a bit of a kickstart in a way? So if only we could non-invasively alter brain function, which leads me nicely into the technique that I'm going to be talking largely about today. So here we have transcranial direct current stimulation. Okay, so just to break it down, so about a third of you indicated that you would be willing to take part in a related experiment at the beginning of the talk. So to break this down, to demystify anything about brain stimulation, First and foremost, this is absolutely not electroconvulsive therapy. Just to dispel anything like that, we may have all seen One Flew Over the Cuckoo's Nest and the harrowing depictions of brain stimulation. And I absolutely understand, and I get that a lot in my research. Individuals think that they might be up for memory loss and seizure induction, and that is absolutely not the case. Couldn't be further from it. We're dealing with incredibly weak electric currents here. So 1 to 2 milliamps is what we're currently using in the lab with our work with older adults. And to put that into context, you would need to multiply that by 6,500 to be able to power a hairdryer. Okay, so we're talking teeny tiny amounts of current. Okay, so absolutely nothing like some of the previously well-known brain stimulation techniques that you might be familiar with. So what we have here, our device on the left-hand side there is effectively a 9-volt battery in a fancy box. Just again, to demystify what's going on here. That is attached to 2 cables. We have a red one and a blue one. So the red one there is known as our positive terminal or anode, and the negative one, the blue one, is known as our cathode. And the electric current flows through the pink cable, through the anode, through the brain to the negative terminal, the cathode there, to complete what is effectively an electrical circuit. So what it does is it changes the way that the neurons in our brain are behaving underneath the pads where you've placed the electrodes there. So what we've got here, we've got our red pad over motor cortex. So this particular depiction is what you would be looking at if you were looking to change somebody's movement, for example. Okay, many other ones that we can do, depending on the type of research question that you have and the area of the brain that you are interested in. So what that feels like to your average participant is a sort of mild tingly itching sensation where the electrode pads are actually positioned. So largely not painful, a little bit uncomfortable and annoying. It feels like you want to give it a really good scratch, but ultimately not a kind of painful procedure. We do have our individuals sitting there with their really super glamorous tDCS device on for a good 10-15 minutes. So it's important that it's comfortable, and our participants do report that once that first minute has gone by where there's a really super tingly, warm, itchy sensation that they feel like they really want to get at, then it's absolutely fine and they tend to forget all about it. So what this then does in terms of the neurobiological effects is to produce a prolonged change in cortical excitability. So we're able to increase the activity of our neurons above the threshold that they would usually need to become active. So we're increasing the likelihood of brain activity by administering these really weak electric currents. And what this does effectively is we can strengthen plasticity with this particular technique. So plasticity being the building blocks of learning, of memory, we can help to essentially rebuild or to sustain cognitive function and plasticity in older adults with this particular technique, which is why my lab in particular feels it's a very strong starting point in order to start to rebuild cognition and ultimately independence and maintain quality of life in older adults. So rather than stand here and show you diagrams of what's going on in the brain when tDCS is actually being delivered, if I could potentially have 2 to 4 volunteers to give a bit more of an interactive demonstration, that would be wonderful. And this isn't signing up for brain stimulation. I already have my guinea pig for that. Yes, thank you so much. 2, do we have up to 4? Oh, perfect. So, which of you would like to be left hemisphere and right hemisphere? Yeah, perfect. So we'll get you standing on the right side to start off with. Who's right? You. Right hemisphere. Who's our left hemisphere? Yes, absolutely. Thank you so much.
Touching on the evidence base for this.
So if I could get these to stand this side. Perfect. There we go. So the corpus callosum isn't that big, so can we switch you together? Perfect. And eventually I will need 2 volunteers to be our active electrode and our passive or our return electrode, our anode and our cathode. Yeah.
Thank you.
So if I could get one of you to hover in the right periphery with our active electrode, it will be your time to shine in just a moment. Over here, yeah. Okay. So we are already familiar then with the very, very basics of tDCS. So as I've mentioned, we have our positive terminal, give us a wave. There we go. And we have our negative terminal as well. Perfect. So we have our aging brain. We have a left hemisphere and we have a right hemisphere. So I come at the kind of typical aging related problems in cognition from the perspective of attentional control. And here what we can see a lot of the time through neuroimaging and through brain scans is that we have a overactive right hemisphere and an underactive left hemisphere. So what we can attempt to do with our tDCS device is to try and rebalance and regulate activity so that it's equal. Okay, so that's effectively what we're trying to do and how tDCS will work. So if we could demonstrate that, can we have a super active right hemisphere, whatever movement, there we go, and a little bit of a sluggish left hemisphere. There we go, perfect. So then when we introduce the tDCS, so if you guys can move into your respective hemispheres, just get a bit closer. Perfect. So what's going to happen? We are going to increase cortical excitability on the left-hand side, and we're going to decrease cortical excitability on the right-hand side. Okay. So theoretically, then, if we give our brains our stimulation, there we go, then we'll start to see her moving in exactly the same pace. So can we coordinate? Yeah. Left. Come on, left hemisphere. Perfect. Thank you so much. I think that demonstration was definitely better. Fab, so you are all tDCS experts now, I've decreed it. Perfect, okay, so then, tDCS in theory. So if our brain stimulation technique can enhance plasticity, and hopefully after that riveting demonstration, we all know that it absolutely can, and then strengthen connections between neuronal populations, it could absolutely be a valuable tool in boosting cognitive performance, okay? That's the theory, that's the setup and the rationale for everything. So where's the evidence? We do have some evidence that we've gathered over in Swansea, where I'm based. And effectively, we can see some benefits in relation to greater, more effective attentional control after just 3 sessions of tDCS, okay? So myself and colleagues have got a number of papers at the moment showing how this all works, largely using what we call the STACK task or the Swansea test of attentional control, which you can see in the centre there. So what the participants have to do, you've got on the right-hand side a target, the little kind of circular donut shape that's highlighted in red. and you have a stream of symbols that will be scrolling up the left-hand side of the screen. And whenever you see the target shape there, you would press the space bar to indicate that you'd seen that. Lovely and simplistic, quite a nice pace to start off with. Then the better you are, the more difficult that task actually gets. So with some of our really high performers, you can see the scroll whizzing past the screen, and you're just trying to monitor between the target, which changes every so often, and the symbols that scroll up the left-hand side. It is quite demanding. It's definitely taxing on your vigilance and your kind of task monitoring capabilities. So a great attentional control task to be using. And what we've seen with this when we apply tDCS before and after on various occasions, so in the graph bottom right there, you can see how our groups were performing at baseline. And we have those individuals who were given an active variant of the stimulation. And we also have a placebo control group as well that didn't receive the stimulation, but went through exactly the same process otherwise. So what you can see in terms of the sham group, performance never really changes from baseline. It oscillates a little bit, perhaps a tiny bit of a practice effect or an exposure to the task over time, but it largely doesn't change between the very beginning and after the third time they've had the brain stimulation. What you can see though, and that lovely gradual change across sessions 1, 2, and 3 in the active group in the red there, is a very definite change over time in terms of the speed of processing. So in terms of the difficulty of the task, by the end of the study, those in the active group were far better at taking on those more rapid speeds and doing very well at the task than those who were in the placebo control group. So there we've got some evidence of enhanced cognitive function in terms of attention mechanisms there.
What was the time period between the stimulation?
So every session was split with a period of 48 hours. So the typical pattern would be that they'd come in for their stimulation on a Monday, a Wednesday, and a Friday.
Blinding in that study, was it double blind or single blind?
It was double blind. So the stimulation device that we use is capable of having codes input into it, so that you don't actually know as the researcher whether you're giving the active or whether you're giving the placebo variant. Perfect. So we've done that. That was a study that was using 20 minutes of stimulation. But of course, if you can get maximal benefits with a less intensive intervention, then absolutely perfect. And we now have data to show that a 10-minute stimulation period should also suffice in getting us this type of effect. So we're not only trying to show that tDCS is capable of cognitive enhancement, we're also actively trying to optimize the technique as well to show what could work best to offer the maximal benefits for trying to bolster cognition in aging participants. So at this point, you might be thinking, okay, why not a memory intervention? Memory was one of the things we spoke about in the very early part of the session about memory loss, memory decline. And there is memory research going on out there in the tDCS community. But I think it's very important to be looking at attentional control, particularly because of the real world benefits that it can actually bring about. So something like being able to inhibit distractions. Distractions are an ever more present part of our lives these days. Having greater attentional control and limiting the ability of our mind to wander off in different directions can make all the difference in a real world scenario. For example, if you're crossing a road, being able to pay attention to the stimuli that you need to be focusing in on and being able to ignore any other distractions around you. So very much within this sphere of research, definite scope for benefits that could have real world implications as well. Perfect. So then, tDCS in practice. So this is the part where I need to ask my lovely colleague Andrea to help me with the demonstration. Thank you so much. So, yeah, hello.
Because you've done over lymphoid gaps.
Yes, yeah.
Have you looked to see if you went pressing them a week or
So the longitudinal element is something that I'm very much interested in, but have yet to dive into due to funding restrictions. So to get them to come back, obviously, would be more visits, more time in the lab. So it's something that I'm actively working on, and I think is incredibly important in terms of building on the attentional control research. In other research, they've shown effects that have been present after, again, a similar amount of stimulation in terms of working memory function that has gone on to be sustained after 1 month. So we do see quite a lengthy time period in terms of the activity that we're able to see right after the stimulation, still translating to at least a month down the line. Perfect. Okay, so
Before you start, can I just
absolutely, thank you, Kim. No, this is absolutely perfect. Yeah, this is brilliant. Okay, so as promised, 9-volt battery in a box. Nothing scary at all. So this is our stimulation device that we will be using. Okay, so first things first, of course, we need to know exactly where to position the pads that we're going to put on our anode and our cathode on the surface of the scalp. So we're going to go for a classic attentional control setup here. So we're going to target what we would refer to as the dorsolateral prefrontal cortex. So that's roughly here and here on the brain, but we need to be a little bit more specific with that. So I have a very glamorous cap with lots of landmarks written on it. So what we'll do now, you're getting a makeover. If you'd like to do that up under your chin, please, so it's nice and snug. So then we just need to make a few points here. Hopefully you won't be walking around with dots on your head for the rest of the day, Andrea. Lovely. Okay, so we can take the cap off. So that's for the purpose of knowing where our brain landmarks are that we need to find. We've got here, we have our little sponges there that our electrodes are placed into. Again, pink and red for our anodes and our cathodes. They are in a little saline solution just to help with the impedance and the current in the scalp. So we're going to pop them in place and make sure that they are secure with these really glamorous bands. So now it looks like you're in an 80s fitness video, Andrea. So we don't want these to be too tight. Does that feel comfortable? Yeah, absolutely fine. Perfect. And as if that wasn't glamorous enough, we're going under the chin with this one as well. I can do that all the time. How's that feeling? Is that secure? All fine. We've got our electrodes. The top two. You can see lovely lovely. So we're going to upregulate, increase cortical excitability on the left-hand side and the dot over there. Yep, under the band. Okay, and the blue one. How are we looking? Okay, so pop the device on. And it's ingenious because you cannot have it plugged into a mains electricity supply while you're also using the device for obvious reasons. We are not in the business of giving people shocks, just mild stimulation. Okay, so I'm just going to enter that code as I mentioned for the stimulation. So as I mentioned, what Andrea should feel in just a moment is a mild tingly itching sensation. Should start to dissipate after the first 30 seconds to a minute. Okay. So, Andrea, are you happy for me to hit go? Okie dokie. And in Andrea's own words. Perfect. Okay. So that should be starting. Any sensations just yet? No. Okay. All okay so far?
I can't tell you now. I've so much coffee to go. I'm sure
You didn't need the brain stimulation today. You're already firing on all cylinders.
Picture.
It is a different kind of configuration. So in the image that I showed, that was for stimulating the motor regions of the brain, whereas this is for the frontal part of the brain.
I can feel something more, just almost slightly.
Okay. How would you describe that?
It just as you say, as if I just want to scratch the front of my head. And it doesn't really the hair is out of place, which is really irritating. I just feel like I want to lose my hair. But that's it.
Nothing. So would you be able to sit like that for the next 15 minutes if we were in the lab?
Yeah.
Yeah. Okay. Lovely. The resounding success in my book. Perfect. Okay, we'll stop there. Pardon? We encourage them not to. You can fidget with your hands or you can move them around if you want to, but we advise not to scratch. Okay.
Do people read during this video? Do something.
What we do is usually we'll pop on a nature documentary so that individuals can be engaged still, but that their mind isn't wandering and they're getting too fatigued, but that they're still very much part of the process. Perfect. Thank you so much, Andrea.
So there was a unit run by 9-volt battery,
Effectively, yeah.
because and obviously it's not shocking like you see in when people or something else.
Yeah.
But thinking back at the child and I used to turn on 9-volt battery because it used to
Yes.
it's not like that because it's more fair.
Yes, absolutely. So as you've noticed as well, these electrode pads are far from teeny tiny, so that dissipates the current across the whole width and length of the electrode. So it's not super targeted and pinpointed, so it does spread the current out so that it's not so focal. Perfect.
I know your research is focused in older adults, but is there any like research into this in like younger children with things such as like ADHD?
Yeah. There is a whole movement in that area as well, definitely. There's so many applications. So aging is where I come at it from, but obviously anything to do with dysregulation in the brain and overactivity in some areas, underactivities in others. Anytime there is scope to regulate that balance, then there's definitely an application for something like tDCS to be useful.
Have people started retailing?
There are some questionable devices out there. There's some that are very much aimed at those who play video games and need to have that kind of locked in vigilant focus. They will market that in terms of having the greatest gaming experience that you possibly could, because they are trying to increase attention. But the downside with that obviously is the lack of regulation. So we use it in a very controlled setting in the lab, and anyone who uses it, my students who come in as part of master's projects, get a lot of training in the safe, effective use. But anyone who just happens to pick up this kit online, for example, they're probably going to put it on and turn it up as far as it will go and stimulate their brains for as long as possible. So it's absolutely not something that I would advocate for, to say the least, but it is out there. In terms of looking at various aspects of cognition, it's something that we currently would screen for. And if we were going to do an ADHD study, that would be perfectly positioned to have those who are experiencing that as well as a control group. But in terms of looking at something like the process of aging, we potentially would screen out for anyone who had attention deficits, simply because they would be regarded as a different group that we would want to focus in on separately. Brilliant. Okay, so hopefully you've been convinced that tDCS is safe and effective, and I've dispelled some of the misconceptions around brain stimulation. So if I can ask for a repeat show of hands, how many people now would consider not signing up today, but consider signing up for a brain stimulation experiment? Yay, thank you. That's wonderful, very much. Most of the room there. Okay, so just to wrap everything up. So in terms of the aging brain, so we know that we can sustain cognition in later life, and it's likely then that methods such as tDCS do and will have their place in the future to try and enhance plasticity. And then tDCS can offer a lot in terms of its capability to build plasticity and to change and improve the way that we can control our attention for real world benefit further down the line. And in terms of application, so it's vital that this type of research keeps ongoing so that we can continue to find improvements and benefits in a range of participant groups, including older adults. And then we have to optimize these benefits for the greater good of our older patients and our communities. So thank you very much for listening to me today. Hopefully you've had a fun and enjoyable talk. And I would like to thank from the bottom of my heart, CADR, for giving me the platform for doing my research and speaking to all of you. Thank you so much. Perfect. Do we have time for questions?
Yeah.
Okay, if anyone's got any burning questions, yeah.
I was thinking about those effects, like, you know, obviously we're all very, very keen now to talk to be involved in research, but what's the rate of adverse effects and what adverse effects are there?
So beyond the immediate tingling, itching sensation, we've only had a couple of reports of participants feeling a little bit nauseous and having headaches in the kind of hour or two after they finished stimulation. Other than that, we are side effect free effectively. So really, really minimal effects that we're dealing with on the large kind of sphere of things.
And I mean, from a sort of like more of a clinical one than a research viewpoint, I mean, are there any kind of exclusions, like people with epilepsy or people with sort of structural brain abnormalities?
Yes, so in the type of research that I've recently been conducting, where we're, and excuse the word normal, but looking at normal aging, healthy aging, we would screen first and foremost for any cognitive impairment to begin with. Again, similar along the lines of the ADHD population, that they would require their own study to be of any benefit there. We do exclude individuals with a seizure history and individuals who are experiencing any neurological deficits as well, simply because we wouldn't want to interfere where things are potentially not as they should be already, until we can get to the stage where we are engaged in research alongside NHS and clinical partners. We would definitely prefer to steer clear of doing more harm than good effectively. Thank you.
So I'm too early to ask this, but where do you see this research affecting other apologies. So where do you see it affecting? Do you see it coming in terms of preventative measures or to minimise, I suppose, some of those risks? Or do you see it as an intervention that maybe reduces or prolonging and maintaining cognitive stimuli as long as we can?
Yeah, I think it could absolutely be both. I am particularly interested in the preventative side of things. So where I've done some research into the technique, I tend to recruit participants who are in their 50s and early 60s, looking at the point where we're starting to see brain changes and changes in cognition to try and increase and enhance plasticity and cognition in that particular age range, which will hopefully safeguard them against later decline. But there is very much a theme as well of using tDCS in participants who already have mild cognitive impairment, Alzheimer's disease. And it does look like, at least in the early and moderate stages, that we can start to reduce deficits to the level that you would expect of a normal, healthy older adult. So there's definitely benefits there in terms of bringing symptoms back down in terms of their severity, but also preventing them from being from their onset as well. Yes. Oh, sorry. Yes, absolutely. That's actually, it's like you've preempted it, but it's something I'm very much interested in at present, is looking at how we can take the technique but benefit those who are potentially most at risk of something like Alzheimer's disease or vascular dementia. And women approaching menopause appear to be that particular target group, as well as those with type 2 diabetes as well. So I'm planning to go along that line. So most definitely an interest of mine. Thank you. Yes.
Do you see that's kind of the stage that GPs would like refer someone to, like your kind of research team? So if they were saying they're having cognitive impairment, would they give them directly your number or like a nursing home kind of thing? Or is it some of the stage where you kind of need more? You know what I mean?
Absolutely. We entirely need a lot more evidence before we get to that stage. That's the dream, effectively, is where we can say that, yes, we've got definitive evidence that this technique is going to be valuable and we can start thinking about it in a widespread intervention capacity. Yeah.
So we'd still be reliant on brain scans to be able to identify the activity for the intervention.
At present, yes. So it would be a case of, well, we're still in the very basic research stages with tDCS at the moment. So in terms of impacting on dementia diagnosis or anything like that, we are years away, but we're aiming big, we're dreaming big. Yeah. In certain populations, so if we were to start to look at interventions at minimising symptoms in Alzheimer's, then most definitely yes. Not the case with our current cohort of healthy ageing. Perfect. Thank you so much, everyone. Thank you.
So what is available in the restaurant, hoping everyone will come back at 1:30 in whichever room they're in for the next section. Thank you all so much.
Thank you.